take this? Who do we have? Friday. Yeah,
Okay.
do you mind if you sit there?
I like the seat better. Thank you for moving.
Okay.
Yes,
And
because
I
you're
like
the,
to be at the corner, I'm the chairman.
yes. We'll switch.
We don't, this doesn't have the program today. Are you the first speaker? Oh, please go up. So let us start and bring up the sheet so that I can see what is the title, because it's in my bag. You have it there. Well, it's the best knowledge we have. We work with the information we have. Okay, here we are. Well, thank you. Yes, so today is the day for the strong people who are still here and still have, after all these sessions we had, and don't forget the evening sessions. And we have to move on. We know life is life. And we will start with Daine, Danielson, black hole decoherence, quantum superpositions. Daine, please.
Well, thank you very much. And thank you to the organizers for having me here. This has really been one of the best conferences I've been to, actually, especially after last night's spectacular musical performance. So I'm going to tell you about some recent work, ongoing work, done with Gautam, Satishchandran, and Bob Wald. Started at the University of Chicago, and now Gautam has gone on to Princeton. And you can read more about everything I'm going to be mentioning in these 3 papers here, as well as some other work done by other groups building on this that I'll mention throughout the talk. And the main takeaway that I want you to get from this is just the fact that black holes are well, what we've shown is that black holes induce decoherence on all quantum superpositions in their exterior by a previously unknown mechanism, which I'll hope to exhibit for you now. So I'm going to begin with a thought experiment, which should convince you that this decoherence effect is present even before I do any calculations. And this is actually the way that late one night, as I was drifting to sleep, that this idea actually, emerged. Is just by this thought experiment. So this is a space-time diagram, and it depicts an experimenter, Alice, who in the distant past has made a quantum superposition, a spatial superposition of a charged body with spin. It could be any massive body as well, but for the sake of brevity, I'm going to be talking about the electromagnetic case. But there's an exactly analogous case that goes through for any massive body in linearized quantum gravity. But I'll just stick to QED for now. So Alice makes the superposition in the distant past, brings it in, and at some predetermined time, she begins to accelerate the branches of her superposition together in order to recombine them. And once the spatial branches of the superposition are overlapping, she's going to attempt an interference experiment and look for signs of decoherence of her superposition. So, for instance, she could do this by looking for coherent interference of the spin. If the spin is superposed in the z direction in this way, then she could perform a measurement in the x direction, and if she even once saw spin down, she would know that her superposition had been decohered by some degree. Okay, so imagine that meanwhile at space-like separations, there's some other experimenter who is going to attempt to become entangled with Alice's superposition. by releasing a particle from a trap and allowing it to evolve in the superposed field. Now, of course, Bob can choose whether to measure or not to measure. And if Bob successfully measures, then by complementarity, Alice had better be decohered. But as I've just explained, it's possible for Alice to tell whether she is decohered. And this seems paradoxical because Bob is at space-like separations, and by this protocol, as I've explained it, it would seem as though Bob could communicate to Alice faster than light. So what are the, obviously, there should be no paradoxes in QED and linearized quantum gravity. Indeed, there are not that I'm aware of. And the resolution in flat spacetime is the following, that there are vacuum fluctuations, which I didn't mention to you, which are a fundamental source of delocalization of Bob's particle in QED. Bob's particle cannot be localized any better than its charge radius. And in quantum gravity, there's a similar argument that one can calculate that a Planck length is the kind of the best that Bob can localize the center of mass degree of freedom of his particle. Simultaneously, Alice can't just recombine her superposition any way that she wants. She has to accelerate the branches of her superposition in order to get it back together, and she's at risk of emitting entangling radiation in the process. So she needs to recombine sufficiently slowly that she doesn't decohere herself. Otherwise, of course, there would be no paradox. And so if Alice goes slower, Bob has to measure from further away to remain at space-like separations. And so it turns out that, and he's trying to measure then a weaker field against this irreducible vacuum fluctuation noise. And it turns out, as we show in this paper in 2022, that these are precisely the ingredients required to ensure the causal consistency of QED and linearized quantum gravity. However, what if Bob was behind a black hole horizon? So then, similar argument, you could run a similar argument. Now, of course, Bob is again at space-like separation from Alice's recombination experiment. Bob had better not be able to signal to Alice from behind a black hole horizon. But now there's no limitation on how long Alice can take to recombine her superposition. Alice now can take if I have a large black hole, eventually Bob will die. So let's say this should not be Bob Wald, my advisor. It should be maybe a robot or something, I don't know. But Bob will eventually die, but if it's a large black hole, Bob will have plenty of time to perform his measurement, and Alice outside will have as long as she likes, the entire lifetime of the universe, to perform her interference measurement. So there doesn't appear to be any obstruction anymore to Alice successfully performing her recombination and mitigating her decoherence that she might induce on herself. So this sounds like the paradox is restored. Now, it occurred to me at the time there would be a resolution to this apparent paradox if a black hole decohered every superposition in its vicinity as though it was filled with optimal measuring Bobs, regardless of whether those Bobs are in fact there. Because then, of course, there could be no signal because Alice learns nothing by decoherence because the black hole itself is responsible regardless of whether there's a Bob. And so, indeed, we show that this is true. We first showed this in 2024, this year, we showed this in these papers that the black hole incurs a constant rate of decoherence on every superposition in its exterior. And in an upcoming paper with our colleague Jonah Kudler-Flam at the Institute for Advanced Study, we show that actually this is precisely the amount of decoherence required to account for any number of bobs performing optimal measurements in the interior of the black hole. So now let's do the calculation and see what actually this looks like. So suppose Alice performs her experiment in a stationary laboratory outside a black hole. Could be using rocket boosters to stay at some fixed radius from the black hole. She's not going to be extremely close to the horizon, otherwise, well, she'd have a lot of, well, she'd be burning up if she was extremely close to the horizon. So she's reasonably far away, and you could ask, why would this be any different from flat space-time? I mean, I've already given you a hint, it should be different, but what's really different about it? So these are just some coordinates. This is kind of a picture, a cartoon of the black hole. I'll be using some angular coordinates. This is the black hole horizon. And big V will correspond to time along, affine time along the horizon of the black hole, and R will be the ordinary short-shield radial coordinate. Alice's laboratory time I'll denote by T, and it's related to the kind of time as measured along the horizon by this exponential relationship. So just to warm up, I'm going to discuss, if you take one half of the superposition, just a classical source of electromagnetic charge, and see what kind of coherent state of the quantized electromagnetic field you get outside the black hole. So if you take Maxwell's equations and you pull them back to the black hole horizon, they take this particularly simple form, which has a nice interpretation. It says that the time derivative of the radial electric field, or the kind of evolving in time Coulomb field of Alice's superposition, or in this, of her particle, becomes equal to, on the horizon, radiation that is falling into the black hole. So these A indices are angular indices tangent to the black hole horizon. So this is kind of radiation modes falling into the black hole through the horizon. Now, the electric field, these angular parts of the electric field, are given by the V derivative of the 4 potential. And what this means is that if you have a net change in the radial part of the electric field, then the time integral of this equation has to be non-zero, which means that the angular part needs to change, or needs to have a net integral, I should say. And that means that the angular part of the 4 potential needs to undergo a permanent displacement between early and late times. There's a net change in the 4 potential. Now, of course, the 4 potential is a gauge field, but changes in the 4 potential are gauge invariant. So what does this look like? If time versus your favorite component of the angular parts of the 4 potential, the 4 potential will begin at some value when the particle is initially at some fixed radius. And then as Alice brings it to a new radius, the particle moves to a new distance, which I'm calling little d away from its original radius, big D. This step function-like behavior at low frequencies is a direct mathematical analog of the electromagnetic or gravitational memory effect at infinity. But now this is taking place on a black hole horizon. Also, for those of you who might be, the memory effect is in some cases particular to 4 dimensions, but everything I'll be saying here happens in any number of dimensions. Of course, I live in 4 dimensions, but some audiences aren't so sure about that. So soft photons on the black hole horizon. Okay, if I if I Fourier transform something with a step function-like behavior, there will be a leading order 1 over omega behavior in Fourier space. Okay, why do I care? Well, the number of photons that are contained in this, the expected number of photons contained in this coherent state of radiation, depends on the Fourier transform of the field. And if I just compute this Fourier transform with a leading order 1 over omega piece, I get actually an infrared divergence. So for a particle that undergoes a permanent displacement outside of a black hole, the number of expected number of photons radiated into the black hole diverges. That again is a direct analog of the memory effect and the infrared divergences that plague computations in QED scattering, but that's a story for another day. But this should already be kind of concerning because this is an infinite amount of quantum information, even though it's arbitrarily low energy. So although these photons can be as low energy as you like, because Alice can perform her experiment as slowly as she likes, the number of particles is diverging. Okay, so I'm not going to have Alice keep her particle displaced strictly forever, because if she does that, when I introduce the other, really I want to consider this superposition experiment, and I need Alice to recombine the branches if I ever want to make a meaningful notion of decoherence. Otherwise, it would just be false decoherence, as Bill Unruh taught us. So I need to, what I'm going to now consider is suppose Alice keeps one branch of her superposition stationary and the other branch she displaces, and then after a time on the horizon delta V, she brings it back and performs her interference experiment. Then, as before, you get this 1 over omega leading order low energy, low frequency behavior. But instead of infinity, you get a logarithmically growing number of photons in time on the horizon. Okay, but here's the perhaps, if someone tells you that they're going to decohere you by some logarithmic amount, you shouldn't necessarily be too worried. That doesn't sound very frightening. But remember the exponential relationship between between time on the horizon and time in Alice's laboratory. So what this means is that in terms of Alice's proper time, the difference between the branches of her experiment will necessarily source in a number of entangling photons that grows linearly in time. And of course, this is going to appear in the exponent of the off-diagonal terms of her reduced density matrix. So in fact, she decoheres exponentially as a function of time in her lab. So for long t, the expected number of photons that are radiated into the black hole is, just by virtue of the fact that she made a superposition at all, regardless of what she did, going to exceed 1 expected photon. And that means that Alice's particle will be decohered after, eventually, no matter what she does. Of course, in all this, she could make it worse for herself. She could move her particle quickly and radiate out to infinity as well, or radiate even more into the black hole as well. But what I'm showing here is that even if she tries to do things as in the optimal possible way, she's decohered by some amount no matter what she does. And by the way, a horizonless object would not do this. I can discuss that more a little bit later. But this really is something special about black holes and horizons more generally. So plugging in the numbers, that Alice's superposition has a coherence time of only 10 to the 43 years in these kind of human scale units. So if our sun were a black hole, an electron on Earth superposed by a meter would decohere in 10 to the 32 times the age of the universe. I wouldn't be too worried about that. I think there's probably some other sources of decoherence that would dominate. But if it were done at the innermost stable orbit of the black hole, it would be down to 5 minutes. Now, of course, even then, for astrophysical black holes, there's likely going to be some accretion disk that would probably dominate over this. But it does get, stronger. I should explain what these constants mean. So d is the distance in Schwarzschild distance from the black hole. That's big D. Little d is the size of the superposition. Q is the charge of the superposition. And m, of course, is the mass of the black hole. And what this is saying is that as you get closer to the black hole, the effect does get much, much stronger because of this sixth power appearing. But I mentioned at the very beginning, this is also true for a massive particle. In fact, it's true for any particle, any quantum mechanical object that has energy, so anything. And the analysis goes through in basically the exact same way, but with a few extra indices floating around. And there's an effect that is a universal effect. Of course, one could argue, well, not everything has electromagnetic charge. I could try to build some perfect Faraday cage. There's no such thing as a Faraday cage for gravity, so all objects, irrespective of their composition and irrespective of circumstances, decohere outside of a black hole at a rate given here. Now, it's microseconds appear here, but then if you look at the rest of the units appearing, you realize this is an incredibly weak effect in the gravitational case. I would need to superpose the entire Earth by its radius outside of a solar mass black hole, 1 AU away, to get this 10 microsecond number, but nevertheless, it's universal. Right. So I mentioned that this, for those of you who might have been thinking along with me here, nothing I've mentioned is that particular to a black hole. The causal argument I gave would have held for any kind of a horizon of this kind, and the calculations I did actually are really only peculiar to a killing horizon, not really to a black hole horizon in particular. So if any horizon where the kind of laboratory notion of time of Alice ends up going null on the horizon, that's a killing horizon, well, assuming Alice is following a killing field, whatever, you'll get the same effect. So in particular, if you consider de Sitter spacetime, like ours appears to be asymptotically approaching something like a de Sitter spacetime, then the horizon radius, given with a horizon radius r, there's a directly analogous effect there. And it scales as I've indicated here. And of course, as long as the superposition is much smaller than the horizon radius, then the decoherence time will be much larger than a Hubble time, unless you have extremely large charges involved or masses involved. Extremely large by quantum mechanical standards, I should say. Nevertheless, this is, besides the fact that this is happening to all of us right now due to our cosmological horizon, but at such a slow rate that I would never hope to measure it, we see that the decoherence is not just a byproduct of acceleration. Those of you who, the astute listener might have thought, well, the superposition is accelerating outside a black hole. Isn't it just due to acceleration that Alice is emitting these photons? No, in this case, Alice's lab is inertial, and you still get the effect. You could ask, okay, well, what is the local description of what's happening? And the description is, as we've explored, and Wilson, Garreau, Dugat, and Chen, Yanbei was here yesterday, I'm not sure if he's here now, have explored, actually this takes place also in well, there's an entirely local description in terms of stimulated emission. And I'll just briefly mention that what's locally happening is that the vacuum outside of a black hole is a peculiar kind of a vacuum. It has a fluctuating electromagnetic dipole or quantum gravitational quadrupole that at low frequencies asymptotes to a constant instead of going to zero. So you have this incredible bath of arbitrarily low energy photons and gravitons in Alice's laboratory, which stimulate the emission of radiation by her superposition. This is quite unusual from ordinary physics perspective, that you get this arbitrarily low energy bath of stimulating radiation. Also, as we explored in a more recent paper, there is no such effect, for instance, in the thermal state in the space-time of a star, or in a global thermal state of Minkowski space-time. Again, that's because those don't have, although they're thermal, they don't have the right low energy behavior of the thermal bath in that particular space-time in order to stimulate this effect. And you could also ask, what happens if if you try to model the internal degrees of freedom, if you tried to replace the black hole by a material body with internal degrees of freedom, could you account for this? And recently, Anna Biggs and Juan Maldacena have taken a look at this, and what they show is, in the electromagnetic case, indeed, it's relatively easy to construct a realistic matter model. Say a chunk of thermal aluminum would do the trick. That would give such an effect, but in the case of the quantum gravitational effect, it appears to be incredibly difficult for something the size of a black hole made of matter to induce an effect this strong. And finally, I'll just mention some nice work by Hongji Wei and Sam Gralla that generalizes this, shows the effect also arises in the presence of a rotating black hole. And they also show some nice kind of connections with the black hole Meissner effect in the extremal case. I think I already mentioned this cosmological situation. So the takeaway is that a black hole or cosmological horizon will eventually decohere any quantum superposition. And we think that may have some fundamental significance for our understanding of black holes, horizons, and decoherence in a theory of quantum gravity. So thank you very much.
Thank you. We have time for questions. Yes?
Thank you. If you have an electron in an atom in a well-defined orbital, it has space coherence because it's necessary for standard quantum mechanics. Would you claim that such an atom, such an electron in the atom, if it's close to a black hole, eventually loses all the coherence property and the chemical properties and somehow vaporizes or whatever, ionizes or I don't know?
So for an object in a bound state, I think what would be susceptible to the decoherence would be the center of mass degree of freedom of the atom. I would say I haven't. There may be effects on the quantum coherence of internal degrees of freedom of bound matter, but I certainly haven't worked it out. There are arguments, I won't go into it now, but there are arguments that one can give that there should be some effects in certain situations, but not in a generic sense of disintegrating atoms or anything like that.
Okay. You want to ask a question?
Well, thank you. This is amazing. Well, I'm trying to make sense of this, and I'm asking if I'm doing this right. So the gist is that, let's say, infinity and the horizon are very different, and so it's like the quirks of the Schwarzschild metric that make infrared stuff having to do with the horizon diverge where it wouldn't in flat space.
That's part of the story. However, as I mentioned briefly, there is no such effect in the exterior in the space-time of a thermal state outside a star, even though that locally analysis lab, that space-time is short shield. So the extra ingredient that's required is the vacuum state of the quantum field that a black hole sets up has this additional low energy part. That also plays a really important role.
Yeah, let me finally make my remark, but probably you heard it personally, but the audience heard it several times. Some of these questions are really depending on what is the meaning of quantum mechanics of the quantum state and so on. And I will not go in details. I see some problems here, and I propose that we discuss this. Thank you very much.
Thank you.